Okay, today we're dealing with the math needed for exam number 2 in materials and methods. So the 3 types of problems we have on this exam are finding the number of framing members, whether they be studs, joists, or rafters. And the method is basically the same except for rafters, where we will calculate one side of the roof of a gable roof and then we have to double it at the end. And then the second kind of problem is insulation R-value math. And it's basically you're just adding up R-value systems. So it's not complicated at all once I show you how that works. And then the third kind of question is basic stair calculations. And this is a little more complicated, but it's not rocket science. And once I kind of walk you through this process, I don't think you'll have too much trouble. Again, there's only going to be about 5 questions on the exam. About 10% of the 50 questions are math questions. So it's not a critical part. It's a significant portion. It's 10%, but it's not the end of the world. Okay, that said, we'll come back to the stair calculations after we've dealt with the framing members and the insulation R values. Okay, so finding the numbers of framing members. Studs are typically spaced at 16 inches on center. It could be different, but it's typically that in most cases. Joists are also typically spaced at 16 inches on center for residential construction. And rafters, well, up north, where we have snow loads to worry about, they typically would be on 16-inch centers also. And they're usually not rafters, actually, they're trusses, because we need engineered roofs because of the life safety issues when a roof collapses. But here in the south, we don't have a lot of snow. So typically we do space the rafters at 24 inches on center, 2 feet on center here in the south. But remember, twice as many. So you're going to have to remember that's the big difference with rafter calculations compared to figuring out how many studs or joists. Okay, so here's the process. We're only going to be focusing on the simplest of systems where there's no corners in the wall, for instance, for studs, no partition pieces in there, no window framing, no door framing. In fact, no corners, like I say, that means the corner part of the framing will be part of the other 2 walls that this wall that we're talking about will fit in between. So it's the simplest version. That said, your first step is you got to have a width of the wall. That'll be listed in the problem. And so whatever the width, the studs always go vertical. So we're talking about measuring side to side, left to right, and what is that width of that wall. We have to convert it in step 1 all to inches. So if you got, 20'6", you got to convert that in the 20 feet part into inches and then add the 6 inches back to it. So let's see, the next step, you will divide that width in inches by 16 inches on center. And if you don't get a nice whole round number, you're going to round it up to the next whole number. And then the third step is you add one more stud for the stud that's at the 0 point of the tape. This system of dividing that width by 16 inches counts everything except the first stud. So you have to add the 0 point stud also onto the thing. Okay, so let's look at an example here. Here we're dealing with studs. Example number 1. How many studs are in a simple 8-foot high wall with no corners, no partitions, no windows or doors? Well, first of all, 8 feet, we don't care what height it is, not at least for figuring out how many studs there are. We need to know it to figure out how long the studs will be. But in our problem, we're not focusing on that. I threw in a number you don't need, but I didn't finish the sentence. It said, if this wall is 37 foot 9 inches wide. So that's a fairly long wall. 37 foot 9, we got to convert that all into inches. So the 9 inch is already inches. So we only have to convert the 37 foot part and then add the 9 inches back. So here in step 1, convert the width of the wall into inches. We take 37 feet times 12 inches per foot, and we end up with 444 inches. And then we add 9 inches to the 444, and now our final number is 453 inches. So that's step 1 right there. Down here in step 2, we're going to divide the 453 inches by 16 inches. So that's what we did. But remember, we're going to have to round it up afterwards. So here we go. 453 divided by 16. Remember, I'm using that little fraction line as a divide by sign. 453 divided by 16 inches per stud gives you 28.3125 studs. Well, you can't have 28.3125 studs. You either have 28 studs or 29 studs. We don't round down, even though you've been taught by math teachers from long ago to, if it's 28.5, that's supposed to be rounded down to 28. Not in construction, because we don't have a board stretcher, we don't have a space stretcher or shrinker. We have to have a whole number of studs. And if you have 28 studs, if you round it down, you're going to have a space that's wider than 16 inches. So we round up. So you'll end up with one space that's less than 16 inches. So that's our answer so far, 29 studs, but that didn't count the 0-point studs. So down in step 3, we're adding one more stud for the one at the 0 point of the tape. So 29 studs plus that 0-point stud, that's 30 studs, and that's your answer. So, these are multiple choice test questions, so you got to get it right, or else nothing helps. So 30 studs, that's your answer. You're going to have a problem just like this on the test, except the numbers will have changed, but it's all going to be 16 inches on center. You still have to convert to inches, and you still have to always round up if you don't have a nice whole number, and you got to add that 0 point always. So this is a common system. Okay, joists. Well, ceiling joists or floor joists, if you're on the ground floor of a 2-story building, you could look up if the framing was open and see the joists for the next floor. But if you're on even a single-story building, you've got ceiling joists, well, up above you, well, those will be the same kind of system, except that they'll be 2x6s maybe instead of 2x12s maybe that you might have for a floor system. They got to be stronger when you got to walk on them. You don't want a lot of bouncing on a floor system. How many joists are in a simple floor system with no stairwell or chimney openings or anything like that if it's 15 foot 2 inches wide? Well, remember, that's perpendicular to the way the joists run across the room. So that's 90 degrees to the run of the joists. So step 1, we convert that. Well, the 2 inches is already inches, so we can set that aside. Take the 15 feet times 12, and you've got 180 inches. And then over here, you take 180 inches plus the 2 inches to add it. Now you got 182 inches. So that's our overall across the room, perpendicular to the direction of the joists. So in step 2, we take that 182 inches, and we, just like before, we divide by 16 inches. So we got 182 inches divided by 16 inches per joist, and you got 11.375 joists. You got to round it up, so now we've got 12 joists. No biggie. That's great. But there's still, just like with the studs, in the joist you have to add the 0-point joist back. So 12 joists plus the 0-point joist, you got 13 joists, and that's your answer. Again, in your multiple choice, you'll find that probably 12 is in there, if that was the problem, because I'm thinking that some people are going to forget to add the 0-point joist. So just be very careful about this. A very simple kind of problem, but you want to make sure that you've got your system down. Do these problems more than once to make sure you really understand them. So, with counting rafters, the system is very similar, except we have to double it, remember? So, how many rafters are in a simple gable roof with no dormer, skylight, or chimney opening if it's a 40-foot long by 15-foot wide building? And you see I've got a hint. Use the 40-foot dimension, because that's going to be 90 degrees to the run of the rafters. So how do we know that? Well, you're not going to want to run a gable roof the 40-foot direction where the rafters are maybe meeting 20 feet in the middle if you've got a 15-foot span there for you. So the practical thing is we will use the 40-foot number for our calculations, because that'll be perpendicular or 90 degrees to the run that the rafters will be making. The rafters will be running across the 15-foot dimension. So that's why we convert the 40-foot, not the 15-foot. You got to know that. You pick the bigger of the two numbers. So step 1, we convert that longer dimension, 40 feet, into inches. Now, there's no inches along with the 40. It's not 40-foot 7 or anything. It's just a nice, even 40 feet. So 40 feet times 12 inches per foot equals 480 inches. So that's just the dimension all by itself. So then, step 2, we divide the length, 480 inches, by 24 inches. And then we'll round up to a whole number. Well, let's see. 480 inches divided by 24 inches per rafter is 20 rafters. Do we just use 20 rafters or do we round it up? Well, if it's exactly 20 rafters like it is here, yes, we use it because it's already a whole number. So the answer is just simply 20 rafters. No rounding necessarily. It's already a whole number. So 20 rafters. We bring that down to step 3. We add 1 for the 0 point of the tape. That still applies here. So 20 rafters plus that extra rafter at the 0 point. Now we've got 21 rafters. And then we have an additional step here with the rafter problems where we have to double it. So we got 21 rafters times 2 sides, because there's 1 on each. Now we've got 42 rafters, and that's your final answer. So that's all there is to this. It's not really too complicated once you get the system down. You convert to inches, you divide by the spacing, whatever it is, 16 inches or 24 inches, and then you round it up if needed, and then you add 1 for the 0 point, rafter, joist, stud. But if it is a rafter, then there's 2 sides, so you have to double it. Okay, so that's enough to work from there. Let's see, let's look at insulation R-value math. So this is not very complicated. The process for insulation R-value math, well, the higher the R-value, the better the insulator. R-values can be added together. They can be, as the building codes say, they can be summed up. That means you can say 2 plus 2 equals 4. That means you can add the different R-value systems. So if the R-value of a 2x4 frame wall is R13, and that's about the best you can get with fiberglass batting, you could bring the total system R-value to R19, if that's what the code requires, by adding 1 thickness of some 4x8 sheets of R6 polystyrene foam insulation to the outside of this wall, just like we do for synthetic stucco anyways. So that math would be R13, that's the 2x4 frame wall system, plus the 1 sheet R6, and you add them together and you get R19. Now you see the little dash between them. That's how R values are typically listed, R-13 and R-6. It's not a minus sign here, so just don't get that thrown off and get that confused. But R13, well, 13 plus 6 is 19. So R13 plus R6 is 19. That's all there is to this. It's not complicated. So an example here, well, I've got 2 of them. What would be your overall R value if you added 2 thicknesses of an R4 polystyrene to an R11 2x4 framed insulated wall system? Okay, well, we got R11 to start with in the 2x4 frame wall, plus R4 again, like a pirate. R. Okay, bad joke. But 11 plus 4 is R19 again, because that's usually the goal we're going for with a lot of these walls nowadays in modern times. Example 2, what would your overall R value be if you added 1 additional thickness of an R13 insulated blanket on top of an attic of blown-in insulation of R19. So we're saying that the initial ceiling in your attic has R19, but you want to increase it by adding an R13 blanket on top of that, and you can do that. And so R19 plus R13 is R32. So this is all there is to it. You're adding the numbers up. If there's 2 sheets being added, like we saw in example 1, well, you've got to add them both. But otherwise, there's nothing else to this. Not complicated. Okay, a relief. And then finally, sucker punching you with stair calculations. Well, no, they're not going to be that complicated. So let's look at them. First of all, you can't go any higher than a 12-foot high climb with stairs without having a landing. Usually, way before you get to 12 feet, you're going to want to have a landing to change direction. But, that's a best practice. And sometimes your head clearance with a beam could be enough to make you have to change directions so that you have the head clearance you need. So 12 feet would be 21 risers generally. When you're talking about a perfect stair system is 7-Eleven, like the convenience store. 7-inch rise per step. And then the width from tip to toe of the step we call the run or the tread width. And that would be 11 inches. So 7-inch rise, 11-inch run. 7-inch riser height, 11-inch treadboard width. Okay, so let's go to a picture here. I like this picture. It's a tan picture like what you'll see for other things. You may see this one show up on your test, just like you'll see tan pictures on your test with framing members to identify. So yes, you have to be able to identify these parts. The 2x12 that is, well, typically at least 3 2x12s put together, spaced apart. To build your stairs will have stringers on them, and those 2x12s will have these notches cut in them, so you'll have little shelves to sit the shelf levels to put these stairs on. So yes, the stringer, you need to understand that, and it has a stringer angle with the horizontal that ranges typically 30 to 32 degrees, sometimes up to 35 degrees maybe of angle in the residential code. They're stricter on the commercial code. And then we talk about the riser height. Up here at the top, that dimension from one step to the other, that's the riser height. It's the unit rise, but we normally talk about it as a riser height. It's the riser. How tall is your riser? And then the other dimension is the unit run, the width of each step from tip to toe as you're walking on them. And they're often made of 2x12s. But that's the tread boards that we stand on. You know, you've got treads on your feet, treads on your tires. That's what touches the ground. You know, that's the horizontal part is the tread. And so that's an important dimension and definition to understand too. We've got the risers and treads, 7 inches and 11 inches in a perfect world. And then the other dimensions on this page, you've got the total rise from one finished floor to the other. That's maybe the first thing you always start with when you're doing stair calculations, is finding that total rise number. The total run sometimes is important for you to figure out if you're trying to make sure you got enough room for your stairs. It might dictate whether you have to change direction just because you're running out of space for stairs. Another thing on this page is that 6'8" clearance level with maybe a beam or something. 6'8", that's 80 inches. So that's an important number we use in the commercial and residential codes. So you should be able to recognize these terms from a picture like this. Okay, so with that, here's a better set of stairs. Let me back up to the other stairs first. This pair of stairs or set of stairs that you see here is atypical. It's not normal because the stringer is attached where the top step on the stringer is even with the finished floor, and that is not normal. What's common, like 95% of the stairs are going to be set up like this, where the stringer is mounted to the header of that framed opening for the stairs or whatever, where your last step off of the stringer is up onto the floor system. That is the vast majority of how stairs are almost always done this way. Not like this picture where it's even with the top. Yeah, there's all kinds of problems with doing it that way. But anyways, so this is the default, and this is what we will use for all of our stair calculations. It's what mostly applies anyways. Now this picture here doesn't list riser height and tread boards. They don't have the word tread or riser, so that's the only problem with this picture. You need to know those terms that are on this page. Tread, the tread boards and the tread widths. The riser boards are if you have a board there to kick your toe against vertically, you know, from step to step, then they're called riser boards. But otherwise, the dimension is that riser height and the tread width for the width of each of those steps. Okay, so that said, we'll use this picture for most everything here as we're going through the calculations. A couple of things I want to point out in this picture. One is that you can count the riser heights here, you know, and I'll do that with my mouse here. One riser height here, another riser here, third riser, fourth riser, fifth riser height. Sixth riser height is that last one as you step up there. So there's 6 riser heights. So automatically I can tell you that there are only 5 tread boards. If the stringer is attached like this, where your last step is up onto the finished floor from the stringer, there always will be one less of the tread boards than there are riser heights. So that's an important thing. It'll help you to answer questions about that. So a couple of stairway terms I've already talked about them, and here they are kind of written down. Stringer, that's the angle, remember, that supports the steps. The stringer angle ranges from 30 to 35 degrees, usually 30 to 32, particularly in commercial construction. The riser, that's the unit vertical rise, has a dimension. And the tread is the unit horizontal run, or of course it's the member that forms the step that you stand on. The rise, or the run, when we say it that way, and I typically will avoid saying it to avoid confusion, but when you see them list the rise and the run, they're talking about the total vertical rise from one finished floor to the next. And the run is the total horizontal run from the top of the stair header out to the tip of the stairs at the bottom, but as a horizontal measurement. I will tend to use total rise and total run just so people don't get confused. But when you see it in texts, in textbooks and stuff, rise and run, they're talking about the overall dimensions. The railings and posts and balusters, they all keep us from falling down the stairs. So that's another aspect of the stairs we're not kind of focusing on here. Okay, I mentioned the first bullet underneath stairway basics. It says the ideal stair ratio is 7 inches riser, a 7-inch riser, and an 11-inch tread board. However, each riser height should be within 1/8 of an inch of each other, so they really want to make them as close as you can together. And 3/8 of an inch is really bad form. You would not pass a building inspection with 3/8 variation. 1/8 variation is best practice. 1/4 inch is actually what is the minimum standard for variation in the steps. But you will find if you've got 1/4 inch variation, people will be tripping on your stairs because everybody just lifts their foot up exactly the amount they need to. So that means you have to divide out that total height, total rise from one finished floor to the next. That vertical dimension has to be into some equal divisions near 7 inches. And the building codes, the IBC for commercial construction, it can be no higher than 7 inches. The residential code allows you to go steeper than that, so then you can do that. So we're going to focus only on the IBC here. Makes the math simpler. No more than a 7-inch rise. And so that'll help us in our calculations. And it's really a best form. Even for residential construction, 7-inch rise is a good maximum to use. So people won't be falling downstairs. Okay, so back to this picture here, just for refreshing. Okay, so the stair calculations. The only 4 things regarding stairway math that we will calculate in exam 2 is probably the first 3, really, but let's look at them. Maybe 4. So the first one, the number of risers. So that's the first thing we calculate. We find out how many risers there will be, and then you can go back and calculate the actual riser height, somewhere close to 7 inches, hopefully. And then the third thing is the number of tread boards that there'll be, number of treads, and then the fourth thing that we may calculate is the tread width itself. So I'll show you that math in here. Okay, so the process, you start with finding the total rise. You find that's in the problem, typically, right off the bat. And you take that total rise and you convert it to inches. That's kind of similar to what we were doing in the other problems here for joists, studs, and rafters, right? There's a similar aspect here to that. That's true. So convert the total rise into inches. So I've got in brackets here T rise for total rise times 12 inches per foot, and that'll give you the total rise in inches. So we haven't changed the number, we just converted it all to inches. And then in step 2, we'll find the number of risers by dividing that total rise number that's in inches by 7 inches. You can't take a foot dimension and divide by inches. They all have to be the same units, you know. So you take the total rise, whatever that number is, it's a bigger number, divide by 7, and that'll give you a number that you need to then round up to the next whole number. That sounds similar to the studs and joists and rafter problems too. That's true. So that part's the same. So again, now you need a whole number of risers. And then we'll go and take that total rise number that we already calculated, and we plug the number of risers that we just figured out into that. So we'll take the riser height and we'll divide by the total number of risers instead of dividing by 7 inches like we did in step 2. Step 2, we divided the total rise by 7 inches. Step 3, we take the total rise number again and we divide by the number of risers that we found in step 2. And that gives us a very specific number. And it's going to be something, because we rounded up, we will get a number less than 7 inches, which would comply with the building code for commercial construction. So now we have that second answer. We know the total number of risers, and we have the riser height. The next step, in step 4 here, we're finding the number of tread boards. Well, all we're going to do is take the total number of risers that we found in step 2, and we're going to subtract 1, because we're picking the default method where the last step is up onto the finished floor from the stringer. So therefore, there will always be one less tread board than there would be otherwise. So it'll just be the number of risers minus 1. So that's what I've got here in step 4 at the end. And then the 5th step, if you were going to find the tread width itself, that was the last thing that could be kind of optional maybe. There's 2 formulas you can use. You can take 18 inches, which comes from taking 7 and 11, 7 inches and 11 inches, and adding them together, and we get 18 inches. We subtract off the actual riser height to give you the tread width. And why does that work? Is because in order to keep, let me go back to a picture here, in order to keep those steps level, you don't want them sloping back or forward. As you increase the riser dimension, you have to decrease the treadboard width. But in our case here, we're decreasing the riser height, so we have to increase the treadboard width in order to keep the stairs level. Otherwise, on this board, as you cut it out, you'll successfully keep making these steps lean. And so that's an important thing that many people don't understand. Okay, so back here, the 18-inch number is the simpler equation. You just take 18 minus the riser height, and they'll give you the treadboard width. Now, it's not quite as accurate as an old carpenter's formula that's called the 25-inch rule, where we take 25 inches instead, subtract 2 times the riser height, and give you the treadboard width. So these are numbers that I'm giving you just for interest's sake. I don't make you calculate the treadboard width on the exam. But really, with all of the things I've given you here today, these are all this is the secret to life to calculating stair calculations. There's weird calculations that can come in, but they're all variations on a theme. These are the basic numbers that you use to calculate stairs. And you might say, well, why do I need to know this? Well, when you're a project manager, you need to understand how to make sure that whoever is building your stairs is doing it right. So you need to know enough to make it stop if it's not right. Okay, so here's my first example. I remember I told you the highest vertical climb you can do on stairs by OSHA and by the building codes is 12 feet. That's a number that's universal. So no higher than 12 feet. So I'm using the longest stairs you can have without having a landing somewhere. So here it says, build commercial stairs with a total rise of 12 foot 0 inches with a maximum unit rise of 7 inches. So we're going to find the number of risers, the riser height, the number of treads, and the treadboard width. Okay, so step 1, convert the total rise into inches. Well, this is pretty straightforward. There's no extra inches to add. So it's just 12 feet times 12 inches. That's 144 inches total rise. Now, in step 2 and step 3, we're going to use that number, 144 inches, twice. So step 2, we find the total number of risers. We've got 144 inches divided by 7 inches, and I end up with 20.57143 risers. Well, we can't use that. We've got to have a whole number of risers, so we must round up to 21 riser heights. So that's the most riser heights you can pretty much have in a stair system, is 21 steps up before having a landing of some kind, of change of direction or something. Step 3, we're going to take that number, the 21 risers that we found, we're going to take that and plug it back in. So 144 inches divided by 21 risers. We're homing in to find the riser height by doing it this way, So 144 inches divided by 21, that gives us 6.857 inches for the riser height. It's almost 6 7/8. It's a little less. But anyways, that's the number. And there was a few more parts of the decimal place, but that was close enough. So that's our riser height. That's an important number. You want all of your steps to be exactly that amount going up as close as you can so that you don't have people tripping. The next step 4, we're finding the number of treads. Well, we could have done that even by the time we got to step 2, right? Because we already have the number of risers and it's just going to be one less. So 21 risers minus 1, that gives you 20 treads. So that's the answer. Not a lot of complication there. You just have to know that you have to subtract 1 when you're trying to find the tread boards, the number of tread boards. So that's as far as we're really going on this test. But step 5, just so you know, you can find the tread width by just taking 18 inches minus the riser height. So you can take 18 inches minus that 6.857 inch number that we just calculated in step 3. And we ended up with 11.143. Now, if we use the 25-inch rule, I threw that in here, 25 minus 2 times 6.857, and we got a little bit different number. And so it's more accurate to use the 25 rule, but it was pretty close, when you consider within the 1/8 of an inch anyway. So you just something to keep and file away or remember someday. Okay. That's example 1. I've got another example here where we're building commercial stairs with a total rise of 9 foot 7 inches. So again, a maximum unit rise of 7 inches, no higher than that. So the first step again, just a repetition really here, except that we do have some extra inches involved. So I wanted to have that in here. So we convert the 9 feet to inches. 9 times 12 is 108 inches. And then we add the 7 inches back. So we have 108 inches plus the 7 inches. So our total rise number is 115 inches. So now that we have that, step 2, we're going to find the number of risers because we're just going to divide that 115 inches by 7. So 115 divided by 7 inches here, that gave us 16.43 risers. Again, even though it's less than 16.5, we don't round down. You could in the residential code, and because we can have a little bit steeper stairs than a 7-inch rise. So you could. I think you're better off if you got the room for the stairs, you might as well make the stairs as easy to climb as possible. So round it up. I say round it up all the time. So we got 17 risers. So now we have that number, 17 risers. We can use that in step 3. We're going to take that 115 inches and divide by 17 risers, and we got 6.765 inches for the riser height, which is just a little bit more than 6 3/4 inches. Okay, so we have that number. Step 4, well, that's just finding the tread boards. So if we had 17 risers, so subtract 1, we got 16 tread boards, the number of treads. And then if you want to find the tread board width, you would take the 18 inches minus this, or you take 25 inches minus that, twice the riser height. And you see there's a little difference again there. But even in this case, it's less than 1/4 inch. So that was example 2. Example 3 is the same idea, but this one's actually more real-worldy, because if you were framing up a house with 8-foot ceilings, 8-foot walls, by the time you have a 2x12 joist system for on top of that for the next floor, you're talking about a 9-foot-1 wall system, maybe. Actually, it could be a little taller than that, but still very similar. So let's take this 9 feet we got to convert, so 108 inches again. Now we're only adding 1 inch. We had with 109 for the overall height, total rise in inches. 109 divided by 7 gave me 15.57 risers. Okay, we round that up to 16. So it's one less riser height than what we just had in the previous problem. So now we can take 109 divided by 16 risers. We end up with 6.8125 inches per riser height. We end up with 15 treads down in step 4, and down in step 5 here we're doing the math for the tread width here. But again, on your exam, you won't have a tread width problem. We'll do with finding the number of risers, the riser height, calculating that, the number of tread boards, but we're not going to deal with the tread width. We could, but I just don't have it on there, so I guess I'm omitting that. Anyways. So that's where we're at with these. Make sure you know these terms. Stairs can get more complicated, but it's just a matter of understanding a few more tricks. So you know a lot about stairs now.